what we had done on last Wednesday was high frequency analysis of our common source amplifier. So we were looking at the following circuit. Where we had EN, R, SIG, like so. R2, R1, here's RD, bear with me a moment while I redraw this thing. Here was CSB, EGS, EGD, CDB, and VF. Okay, here's VDD, and here is also VDD. So we look at this circuit, common source amplifier, fully biased, with the inclusion of a signal resistance and all of our parasitic internal capacitances from the MOSFET taken into account. And after a couple of simplifications, we analyzed the following small signal equivalent circuit, where we had a Thevenin equivalent voltage VThev in series with a Thevenin equivalent resistance RThev. And then at our gate terminal, we saw the capacitance CGS like so, over which a voltage drop VGS occurs. Over here at our drain, we had GM VGS in parallel with RD, in parallel with CDB. Here's our gate node, here's our drain node. Here's V out. Down here is our source, which was grounded. And the presence of this capacitor that I'm about to draw here, CGD, made the determination of our transfer function just a wild nightmare, involving a second order polynomial that had all kinds of weird stuff, lots and lots of math and all that kind of jazz, right? So what our first topic of today is going to be about is what's called the Miller method, wherein we can take a circuit like this, where we have a known transfer function between this point in our circuit, which is the gate, and this point in our circuit, which is the drain. So if we have a known transfer function between the gate and drain, with that impedance not being there, we can use that known quantity to divide our capacitor or our feedback element into two distinct impedances based on a certain set of rules. So let's define those rules by talking about Miller's theorem. So let's say that we have a portion of a circuit, right? Where this is going to be node 1 on the left-hand side, and there is some voltage V1. And then way over here on the right-hand side, we're going to have a node 2, where the voltage V2 is equal to K times V1, okay? So that there's some transfer function between node 1 and node 2. Some amount of effectively gain or attenuation is applied between this. Connecting nodes 1 and node 2 is a floating impedance, Z, like so. All right. And there is a common current of I that is leaving node 1 and entering node 2. So Miller's theorem states that for a section of a circuit where the voltage at node 2 is related to the voltage at node 1 by a simple relationship like V2 is equal to K times V1, Z, the floating impedance, can be replaced by two impedances, Z1 and Z2, connected between node 1 and ground and node 2 and ground, where Z1, actually, let's write it like a transformation effectively. So we would have node 1, Z1, here's Z2, and here's ground. Here's node 2. And that same voltage relationship, V1 exists, and V2 is equal to KV1. And we have a current I1 that's equal to I, and we have a current I2 that's equal to I. So we're effectively learning how to perform this transformation where we can split that floating impedance up into two impedances, one connected on the input side and one connected on the output side, okay? So in the left-hand circuit, the only way that node 1 feels the impedance Z is by the amount of current that's drawn away from node 1. So we have to choose a Z1 that draws that same amount of current away so that there's no distinction in what node 1 sees, okay? So our current I1 is V1 over Z1, just using good old Ohm's law. And this has to be identical to our current I in our left-hand circuit, which is given by V1 minus V2 or minus K V1 divided by Z. And we can rearrange this just a little bit. So this is going to be V1 times a factor of 1 minus K over Z. And from this, the impedance Z1 must then simply be our floating impedance Z divided by a factor of 1 minus K. So an impedance of Z1 is equal to Z over 1 minus K causes this impedance to literally draw the same amount of current away from node 1 while keeping this voltage V1 to be the same thing. So it's electrically equivalent, right? We're going to do something similar at node 2, right? So we need a current of I2 to be equal to I. So sorry, let me rewrite this to where it doesn't look so much like the number 1. So our current I2 is negative V2 over Z2, right? Because we want the current to flow out of the negative polarity terminal and head towards a positive polarity terminal. Negative V2 is negative KV1. And this, sorry, that 2 doesn't look 2-ish enough to me. There we go. And this current also has to be equal to I, which we know to be V1 times 1 minus K over Z from the expression above. So what we're going to do here is very similar, right? We're going to divide this expression by K and this expression by K to get an equivalence in the impedances, right? So what we will find there is that V2 is equal to negative K times Z divided by 1 minus K, which is the same as Z over 1 minus 1 over K. One thing here, I'm just trying to double check to make sure I'm not playing too fast and loose with my negative sign. Okay, I know. So the reason why that negative sign gets canceled out, so when I divide this guy by K, I have 1 over K minus K. And when I rearrange those guys, it gets rid of that negative sign. Okay. So this is what my Z1 and Z2 impedances come out to be using Miller's theorem. All right. So I'm going to put boxes around those just real quick. And then we're going to look up here. Node G is node 1 in our Miller's theorem approximation, and D is node 2. So we're looking for a transfer function between G and D. Well, this is a common source amplifier where without all this other crap connected, the gate node is our input and the drain node is our output. So the relationship between the input and the output is just the gain of our common source amplifier, negative GM RD. So negative GM RD is K here. Okay, so that's our relationship between G and D. So from that, our circuit using Miller's theorem is going to look like this, where we have V Thevenin R Thevenin. Here's CGS. And then we're going to have a contribution from CGD, which was our feedback resistor, or excuse me, feedback capacitor, which we're splitting up. So I'm going to call that CGD in because it's on the input side. And then over here, we're going to have GM VGS in parallel with RD in parallel with CDB in parallel with CGD out. So the contribution that shows up on the output side. Ground. And then here's our output node. And so the first thing we're going to do is figure out what CGD in and CGD out are, right? Because Miller's theorem lets us split up the impedance, not the capacitance itself, okay? So 1 over S CGD in has to be 1 over S CGD times 1 minus K, which is going to be 1 plus GMRD. So to be clear here, this is ZGD divided by 1 minus negative GMRD. And so in essence, we see that the capacitance effectively gets amplified at the input, right? Because it's being scaled by a factor of 1 plus GMRD. So the capacitance appears larger at the input term. And then from this, CGD in is simply CGD times a factor of 1 plus GMRD. We can say similarly that 1 over S CGD out is 1 over S CGD, sorry, CGD times 1 plus 1 over GMRD, well, that's just ZGD over 1 minus 1 over K, right? And therefore, CGD out is simply CGD times 1 plus 1 over GMRD. So we're scaling that capacitance as well, but it's being scaled by a very small number, right? Because it's 1 plus 1 over something that tends to be kind of large. So an amplified version of that capacitance gets moved to the input, and something very close to the capacitance by itself appears at the output term. Does that seem okay there? All right. And so at this point, we can get to determining our transfer function, right? So I need to put VGS right here because I forgot to do it earlier. So how are we going to develop our transfer function for this split up system? It's actually much easier than it was previous, right? So our input voltage V7 is related to this quantity VGS using voltage division. So we're obviously going to come up with some sort of voltage division equation there. And our output voltage is going to be dependent on the fact that this current GM VGS flows through the parallel combination of RD, CDB, and CGD out. So our analysis looks a lot more like what we did in 335 than what we did last week by applying Miller's method to break that feedback capacitor up into two parts, okay? So our voltage division relationship, we're going to have VGS is equal to Vthevenin multiplied by CGS in parallel with CGD in, right? So that's just going to look like that impedance. So that's going to be 1 over S CGS plus CGD times 1 plus GMRD. Divided by R Thev plus whatever's in the numerator there. Oh, and I should have a second parentheses there. So CGS plus CGD times 1 plus GMRD, close parentheses, close parentheses. All right, so to be clear here, because there were some looks of confusion, the numerator here simply represents these two parallel impedances combined together, where we know that we can just have, whenever we have capacitors in parallel, they add like resistors in series, and then we're just taking 1 over SC equivalent. Okay. Adam back there? Sorry, confusing you. You haven't done this step in 2. And then in the denominator here, it's obviously just R7 in series with that parallel combination of capacitors. Okay. Now we can make this slightly less ugly by multiplying through by a factor of S, CGS, blah, blah, blah in the numerator and denominator. And so what that's going to give us is Vthevenin times a factor of 1 over 1 plus S R Thev CGS plus CGD 1 plus GM RD. Like so. So we have a transfer function between V7 and VGS where we can clearly identify one of our poles right out of the gate, which is much less horrifying looking than what we had last week.
Okay, so I understand for the CGD in the house, like, is it the Z over 1 minus K?
Yeah.
But what is, how did you get DM or DA? Like, what, I don't understand your.
That's the gain between the gate and the drain for a common source amplifier. That's literally, that's it, yeah. So if we throw, all we're looking for, let me go back here, okay? All we're looking for is some scaling factor that relates the voltage at our input, the gate, to the voltage at our output, the drain. For a common source amplifier where the input is applied at the gate and the output is taken at the drain, That transfer function is just the gain of the common source amplifier itself, negative GMRD. So we're just looking for the relationship between those two nodes. What's connected to the nodes isn't particularly important, other than there being a feedback impedance between those two nodes that we're trying to split up. As we'll see with a common gate amplifier, there is no feedback impedance, so we can't use the Miller method to mess with. That's for some Friday. All right, so we've got this first transfer function. Do we feel reasonable about it? Okay. Just voltage division and then a simplification to get rid of so many damn fractions inside of fractions. All right. For our next transfer function, we're simply going to try to relate the quantity V out to VGS, which, as I mentioned previously, this is a current that has to split and flow between these three impedances. So we're just going to use Ohm's law, right? So our output voltage V out is equal to negative GM VGS times these three impedances in parallel. Okay. So when I have RD in parallel with those two capacitors, that's going to look like RD over S CDB plus CGD times 1 plus 1 over GMRD. And then in the denominator of that is going to look like RD plus 1 over S. Sorry, I needed another parentheses there. CDB plus CGD times 1 plus 1 over GMRD, close there. And I can multiply through by this bit over this bit again, like the SCDB plus CGD, blah, 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 over that same thing to clear out my fractions within fractions. And what that's going to give me, I'll do it down here so I don't run out of space, is negative GM VGS times a factor of RD over 1 plus SRD times CDB plus CGD times 1 plus 1 over GMRD. How do we feel about that transfer function? So we're relating VGS to V out. Over here, we were relating VGS to V7. We're effectively now just going to combine those two relationships, right? So if we substitute in our relationship for VGS up here, and we're going to divide both sides by V7, what we will have is V out over V7 is equal to negative GMRD divided by 1 plus S R-Thav, CGS plus CGD times 1 plus GMRD and then 1 plus SRD CDB plus CGD 1 plus 1 over GMRD, like so. We effectively have the exact form that we're looking for, right? We are technically missing something here from the transfer function in as much as we don't have the relationship for VFAV to VN, but that is the exact same relationship that we had before we did our Miller breaking up that floating impedance on Wednesday. So that part of the analysis is exactly the same. And so we can see now that we have the midband gain divided by two first order polynomials from which we can easily determine our new pole frequency. So from this, omega P1 is 1 over R-Thav times CGS plus CGD 1 plus GMRD, and omega P2 is 1 over RD CDB plus CGD 1 plus 1 over This is an approximation, okay? In doing this, we somehow magically got rid of a zero, right? If you look back at our direct analysis where node G and node D were linked together by that capacitance CGD, we absolutely still had two poles that were effectively coupled together. We had a quadratic response that we needed to figure out what those values were. But we also had a zero in our numerator that we had to contend with. Splitting this up has given us an approximation of where the poles are going to occur in our response, but it has eliminated that zero that we had there. So we have a true second order response as opposed to a second order response where a portion of it gets corrected by that zero. So this is just an approximation, but it's a pretty reasonable estimate of how this thing is going to behave. All right, so the next thing that we are going to talk about, wrapping up our high frequency analysis of our common source amplifier, is what's called the open circuit time constant method. Okay, so in our low frequency analysis, we were able to estimate where the midband began by using a short circuit time constant analysis. We can estimate where the midband ends by using an open circuit time constant analysis, where effectively we analyze our circuit with each and see what resistance is connected to each individual capacitance while open circuiting all of the other capacitors. So it's extraordinarily similar to what we did previously at the low frequency analysis, except that now we are open circuiting all of our capacitors not of interest instead of short circuiting, right? So our open circuit time constant method if you'll allow me to copy and paste something real quick here just for reference. we're going to be looking at our small signal equivalent circuit here. So it's this representation at which we're going to apply our open circuit time constant now. Okay. So first, we're going to look at what CGS sees. Okay. So CGS sees. So here's CGS. This node down here is grounded. Here's GM VGS. Our voltage drop VGS occurs here. Here is RD. Here is our Thev. And recall that we need to short circuit our input. Oh. So what is the resistance seen by capacitor CGS? Just our Thev. So it's literally just this guy right here. And so tau GS is simply CGS times R Thev, or CGS times R sig in parallel with R1 in parallel with R2, if my memory serves me correct. Definitely CGS times R Thev. The question there is whether I'm remembering what R Thev actually is from a week ago. Any questions, comments, concerns about the analysis that we did here? All of this bit right here shorts itself out. It does not contribute to the resistance in any way, shape, or form, right? So effectively, if we tied, just to be clear here, those two ground nodes together and look in through the capacitor's open circuited terminals, all we would see is the Thevenin equivalent resistance. All right. So what does CGD see? So CGD is my capacitor here. CGS is open circuited, so I'm just going to see R Thev on this side. Here's GM VGS. Well, VGS is the voltage drop between the gate node and our source, which is grounded. So VGS is actually the voltage drop over R Thev now. And then here is RD. And this is ground. So we obviously have a dependent source in the mix here. So we're going to need to apply a test source method to determine the equivalent resistance seen by capacitance, CGD. That sounds reasonable. only way that I know of to do this. So let's look at what we're going to have. I'm going to reorganize this guy a little bit to try to make things more circuits one looking so that my brain can comprehend it, okay? So I'm going to put my test source voltage where my capacitor CGB is, okay? So here's my voltage V test, where I'm arbitrarily choosing the positive polarity terminal here and the negative polarity terminal over here. So between the positive polarity terminal and ground, I have the resistance R Thevenin. Then between the negative polarity terminal and ground, I have GM VGS current source. And the current is flowing from the negative polarity terminal to ground. So that's going to look like this, GM VGS. Then I also have the resistor RD. And I'm trying to determine the ratio of V test to I test. So let's start by asking the question, does this look like me applying the test source method to this, where I'm replacing my capacitor CGB with a test voltage source? Everybody in agreement that these two things are effectively the same? Anybody need an explanation there? I know it looks significantly different, but I believe I've got everything connected between the correct nodes. Okay. So what are we going to do here? Well, I am going to apply Kirchhoff's voltage law. So it looks like here, okay? Oh, also one last thing that I do need to point out. VGS, because I don't have it drawn here, is between the positive polarity terminal. So here is VGS like so. All right. So if I apply Kirchhoff's voltage law, I'm going to start at the bottom left-hand corner, just like I did way back in circuits 1. And I have negative V test. And then the voltage drop over R Thevenin, which is simply I test times R Thevenin. And then I need the voltage drop over resistor RD, which requires me to know the current flowing through resistor RD. So if we apply Kirchhoff's current law at this node, we have a current of I test flowing in, GM VGS flowing in. Those are going to combine together and flow through RD. And so I'm going to have plus RD times I test plus GM VGS. So GM and then VGS is simply R Thev times I test. All of these combine together to make 0. Make sure I'm wrapping my head around this correctly. This voltage drop, and this voltage drop. So I close the loop. And I'm saying the current that's flowing through my resistor RD is a combination of I test and GM/VGS together. Yes, sir.
Why would, so when we did our Kirchhoff's current law there, why did none of those currents flow to ground?
Fantastic question. So let's think about things here really quickly. All right, so yeah, I mean, I'm simply treating it as just a node point there. So like it's my source terminal that just happens to be grounded, but I don't really have a better reason than that, if I'm being entirely honest.
Well, I do agree that RD should have current flow through because the node that is not grounded should arguably have a non-zero potential.
Right.
So I guess it's just an analysis issue.
No, and I definitely, I understand that. So having that labeled as ground right there, maybe doing KVL around the loop as I've done previously, might not be the best analysis method to use. Nodal analysis or perhaps mesh analysis might be a better way to explain what's going on, wherein I won't have to worry about that ground. The only potential issue if we did mesh analysis here would be that dependent source in the middle. But that's really actually not going to mess things up. Let's scratch this. Let's do mesh analysis so that we don't have to worry about that ground and see what falls out. I'd be willing to bet we're going to get the exact same result, but it'll be a more robust solution where there's less ambiguity. Okay. So if we were to do mesh analysis here, so let's call this guy mesh current IA, and this guy mesh current IB, right? We can see intuitively that IB minus IA is equal to GM/VGS. And we know that VGS is just R thev times IA. So that's going to look like GM R thev IA. And so what I'm going to do here really quickly then is I'm going to rearrange this expression to put IB only in terms of IA, right? So that would give me IB is equal to IA times 1 plus GM R thev. Is everybody okay with it? Any odd analysis or hiccups or anything there? Okay. So from here, we would apply Kirchhoff's voltage law around that outside loop again, right? So we would have, and IA is obviously the quantity I test as well, just for those of you who are paying attention. So that's going to look like negative V test plus R thev IA plus RD times IB which is simply IA times 1 plus GM R thev is equal to 0. So what I'm going to do now is just move V test to the other side of the equal sign and then divide by both sides by IA. And I'm going to do that up here so I don't have to go to the next page yet. So V test over IA is going to look like R thev plus 1 plus GM R thev times RD. Yep. Thought so. Just less ambiguous, but it is literally the exact same result. All right, so from that result, sorry, too far there. Tau GD is equal to CGD times R thev plus 1 plus GM R thev RD, like so. So lastly, we have what CDB sees, okay? So CDB is going to be our only capacitor of interest. And then we are going to open circuit all of our other capacitors. So on the input side here, we're going to have R thev, actually just R thev. CGS is open circuited, CGD is open circuited. So over here, we are going to have GM VGS, where VGS is this voltage, in parallel with RD, in parallel with CDB. Like so. So what's the resistance seen by CDB? I disagree.
Oh, no. it's RD.
It's just RD because VGS is 0. And so tau dB is simply, bless you, CDB times RD. All right, so we've, yes,
Maybe a stupid question. What is this power movement like?
time constant.
Time constant.
Yeah, so this is an open circuit time constant method. So circling back around to that, in our low frequency analysis using the short circuit time constant method, we effectively added all of our reciprocals together, right? So let me pull it up in my notes very explicitly so that I'm not going to make a mistake here. Did I leave them upstairs? to write it. Sorry. So for our short circuit time constant method, we had omega low was equal to one over tau one plus 1 over tau 2, etc., all the way out to 1 over tau 3. Omega high is determined slightly differently, where it is 1 over tau 1 plus tau 2 all the way out to tau 3. So instead of summing the reciprocals, we're taking the reciprocal of the sum. So it's a different thing slightly. So do you see the difference is subtle, but it is absolutely there as to what we're doing. Okay. So we can estimate that the mid-band ends at a frequency omega high that is equal to 1 over CGS RThev plus CDB RD plus CGD RThev plus 1 plus GM RThev RD. Again, this does not give us any information whatsoever about the actual high frequency response of our amplifier circuit. It is treating it as if we have a dominant pole so that we have a simple first order response beyond this pole frequency. So all it's good at doing is estimating where the midband ends, not about telling us anything about the behavior beyond the midband. Okay. So this is just a quick and dirty way. So effectively, you could use the method of short circuit time constants to tell you where the midband begins, the method of open circuit time constants to tell you where the midband ends, and effectively take the difference of those two things to give you a good estimation as to what the bandwidth of your amplifier is. That's what this concept and the low frequency equivalent method of short circuit time constants is used for. Estimating our bandwidth to say whether or not our excitation frequency of interest will actually result in a good amplifier behavior for us or not any actual characteristics of the response in those regions. Okay, so we have analyzed this particular circuit 6 ways from Sunday. I think literally 6 different ways. Okay, we have beat it to death. We are done with this one. And now that we have been introduced to all of these different methods, we can go through the remaining amplifier circuits in what I hope to be a much more expedited process. Okay, so I'm going to give you a homework assignment on strictly common source amplifiers, where I'm going to ask you to do things. So one thing that I could potentially do here is put an output network containing a capacitor and resistor at the output and ask you to figure out, what kind of pole and zero would be associated with that, and or use the short circuit time constant method to see if that inclusion of a capacitor and resistor at the output node, how that influences where the midband begins or something like that. If I put that loading network on there for high frequency circuit analysis, what would that do? So that capacitor C out would look like a short circuit, and that resistance R load would be in parallel with RD effectively. So that's the level of complexity that I'm expecting. Like that would be the hardest type of things that I could ask you is, let's add that little output network like you had on your design project and see how that influences the frequency response. It's just another transfer function to include that is literally a simple voltage divider circuit that will give you, I think, one more zero and definitely one more pole. So, all right, that's enough out of me.
Any chance you could add the previous videos to Moodle or YouTube?
I'm sorry, what was that?
Add the other the previous lessons from since the last test to
Oh, yeah,
Moodle.
no, absolutely. Yes, I will get off my lazy butt and start uploading videos this afternoon and try to get caught up to literally today's video before we have class on Friday. Does that sound reasonable?
Yep, sounds good to me.
All righty. See you all on Friday.